Let's get started. So today's presentation is going to be on smart high resistance grounding technology, maximizing your protection and ensuring process continuity. So why is there such an issue with grounding concerns? And this is from one insurance company who reported 228 losses over a 7-year period, and the average of all the losses was $769,000, a total of $120 million in losses. And you can see the difference between industrial and commercial systems. So ground faults are prevalent. They're in the industry, in our electrical systems all the time. And there's a lot of losses that come from ground faults due to wastage of material, loss of equipment damage. There's so many different things that come from ground faults. And we're going to discuss how the grounding systems affect ground faults. So ground faults, they say, is the most typical fault that you can have in an electrical system. And some say over 95% of all faults begin as single phase to ground faults, and they propagate to a phase-to-phase or three-phase fault, and then you have an arc flash event. And we can discuss that to some extent. And John, you mentioned you have Z462 and 70E training. Z462 and 70E both state that high resistance grounding is an arc flash mitigation technique. And we're going to discuss that to some extent. So types of grounding on the system in the world used today: ungrounded systems, low resistance grounded systems, solidly grounded systems, and high resistance grounded systems. And you can see that the change or the usage of each of those. So we've gone to our marketplace and we've come up with an electrical risk meter with questions to our audience. So unscheduled process interruptions on the first fault, typically 7,000 to 30,000 is A. The ability to locate the first ground fault in a timely manner. Loss of critical process due to power interruption, capital equipment damage, on average greater than $45,000, arc flash hazards and arc flash hazards magnitude. So when you add up all these numbers, you come up with a risk assessment. So we're going to start with ungrounded systems first, because most systems were ungrounded systems. So there's no intentional ground connection between the system conductors and ground. Ungrounded systems are susceptible to buildup of high voltages, up to 6 to 8 times normal system voltage phase to ground that were typically phase to phase. So if on a 480, 600 volt system, you can easily get up to 6 to 8 times the over voltages with respect to ground when you have an intermittent ground fault. Code requires ungrounded systems to be equipped with suitable ground detection systems. So there is no ground fault protection in an ungrounded system. The only thing you could possibly have in an ungrounded system is ground fault detection. So when we put the meter to it, unscheduled process is very low. You can't have, you should not have any interruption in your power system when you have an ungrounded system, because you can't, the only thing you do is detect the presence of a ground fault. You can't find where that ground fault is, because in order to find where the ground fault is, you have to have power interruptions and find where the ground fault is downstream. Loss of critical processes on the second ground fault, because you don't know where the first ground fault is. Electricians tend to not worry about where the ground fault is because they can't find it. Chances are you're going to get a second ground fault, and the second ground fault can come from deteriorating insulation in other areas, or a timed second ground fault. So you can have 2 ground faults on the same system. Equipment damage is high. Arc flash frequency probability is medium, and the arc flash hazard for destructive arc current is high, because you can't find where the first fault is. You have phase to ground potentials that are phase to phase. On the unfaulted phases, you may have a second ground fault occur and an arc flash event. So on the risk assessment meter, we have a number of 26. Some of the standards that are out there, the Buff Book, IEEE Standard 242, 2001, says that ungrounded low voltage systems employ ground detectors to indicate the ground fault. These detectors show existence of a ground fault, but do not locate the ground fault. Again, the only way you can locate the ground fault on an ungrounded system is to cycle the power on individual breakers until you find the presence of that fault. You have ground fault detection. When that ground fault detection goes away, you keep following that path downstream to find where the ground fault is. Standard 242, the Buff Book, if ground faults are intermittent or allowed to continue, the system could be subject to possible severe overvoltages to ground, which could be as high as 6 to 8 times. And the reason I think it's 6 to 8 times, because if you look at a normal 480 volt system or 600 volt system that we have, 6 to 8 times seems to be around the same mark as 2.2 kV, where we typically test low voltage equipment for high pot. Above that, something is going to fail. The Red Book, IEEE Standard 141, says that overvoltage incidences associated with ungrounded operation reduce the useful life of insulation. Air is an insulation, right? So if you stress the air, you're going to weaken the insulation, and if you have a ground fault, chances are you have a little bit of arcing and it deteriorates the insulation. The overvoltage is caused by Beeman's book. This is an example right out of Beeman's book. So you can see that if you have a 3-phase system, when you have an intermittent arcing fault on an ungrounded system, on the first occurrence of a ground fault, let's say it's on A phase, A and ground are at the same potential. 1/2 cycle later, because there's no grounding system, all you're doing is charging the capacitance of the system. 1/2 cycle later, you're at 2 per unit on A phase with respect to ground. On the ungrounded system, you don't have a dead short to ground, but you have a deterioration of the insulation, so it sparks over. And when it sparks over, that gap created by the weakness in the insulation, now you're down 2 per unit. And now 1/2 cycle later, you're at 3 per unit. And this keeps going on until your whole system collapses. So there's a case study in Michigan where they looked at an ungrounded system, and they noted that they had 485 events of peak voltages above 700 volts due to intermittent ground faults. And the peak voltage was at 1,050 volts. And this transient led to insulation damage. Same thing in a medium voltage type of system. These are surge capacitors, and they fail due to the overvoltages caused by an ungrounded system. Even FM Global, the insurance company, who used to give out discounts to people that had high resistance grounded systems to move from an ungrounded system to a different type of systems, because they realized that ungrounded systems, you inherently get more damage to the system because ground faults are prevalent. And when they are prevalent, you tend to have more ground faults and more damage due to the ground fault. And the inability to locate the ground fault means that they're on the system for longer periods of time. So in ungrounded systems, a phase to ground fault often produces dangerous overvoltage, which we just saw from Beeman's book. Sustained arcing faults in low voltage apparatus are often initiated by a single phase to ground fault. So obviously all faults begin as single phase to ground faults. Unlike an ungrounded system, high resistance grounded systems prevent transient overvoltage. So this is FM Global's way of saying, okay, ungrounded systems are bad, let's move to something else. And the easiest thing to do from an ungrounded system is transition to a high resistance grounded system, depending on the system voltages. For sure, if you have a low voltage system under 5 kV, you can transition to a high resistance grounded system very easily. So their recommendation is to convert an ungrounded system to a high resistance grounded system. So we're going to discuss solidly grounded systems now. So 70E and Z462, employers, facility owners, and managers who have responsibility for facilities and installations having electrical energy as a potential hazard to employees and other personnel should ensure that electrical hazard risk assessments are performed during the design and operation of the system. So the risk assessment involves three things: reducing the likelihood of exposure of a ground fault, reducing the magnitude or severity of exposure, and enabling achievement of electrical safe work condition. Going back to the Buff book, one disadvantage of solid ground system involves the high magnitude of destructive arcing ground fault current. You have to keep in mind that when you have a ground fault in an electrical system, that ground fault current has to return back to the source. There is no impedance in that ground fault. The only impedance you have is the impedance of the transformer and the impedance of the ground fault itself. So you're going to have a great magnitude of current flowing in that ground fault. And this is what was meant by high destructive current. You can easily get 20, 30, 40,000 amps in a ground fault. And the National Electrical Code, either National Electrical Code, the Canadian Electrical Code, and the National Electrical Code in the US state that you have to trip when you have a ground fault on system voltages greater than 150 volts to ground, greater than 1,000 amps. So if you have a system that's greater than 150 volts to ground, you have to have ground fault protection. And as engineers as we are, we always try to strive to meet the minimum requirement. So when we have ground fault protection, we put it on the main breaker. You have a ground fault, you trip the main breaker. Solid ground systems have a high probability of escalating to phase faults. Now you have 40, 50,000 amps of arcing of current flowing through a ground fault. You're going to deteriorate the insulation. You have molten copper or aluminum, molten steel, debris. That's going to deteriorate the insulation between the phases. And when you deteriorate the insulation between the phases, you've now converted that ground fault into a phase-to-phase fault, and it could develop into a three-phase fault. This is why ground faults on solidly grounded systems can propagate to a three-phase fault very quickly if you don't trip right away. Here's an example of a single phase to ground fault that propagated to a three-phase fault very quickly, and it caused $400,000 in damage. Well, this one was much, much more, because what happens now is you lose your electrical switchgear, your main distribution system, so that has to come out and be replaced. You're on generation for a little while, and now we haven't taken into effect the impact on your business. We've only looked at the cost of replacing the equipment and modifying your electrical system so you can run temporarily until you get new equipment. So we applied the safety meter to this. Unscheduled process interruptions. You don't know when you're going to have a ground fault. And when you do have a ground fault, you're going to trip. So that's very high. You are able to isolate the first fault because you have ground fault protection. Now it just matters of how much of your system are you going to lose. If you put ground fault protection on each one of your feeders, you're going to lose a small part of your feeder. However, if you just put ground fault protection on the main breaker, you're going to lose the entire system. Loss of critical process due to power interruptions is low. Capital equipment is fairly high because you still have to replace a piece of equipment when due to a ground fault, because you have 40,000 amps of current flowing at that piece of equipment that is faulted. So if it was an air conditioning unit, you probably have to replace some portions of the electrical equipment. If it was a large motor that was faulted, you have to replace that large motor. The arc flash hazard is high, and the frequency is high, and the magnitude is high. So now we're at 26. So this is how it's assessed in this meter. So there was a local university that looked at arcing faults. And when they measured arcing current here on this scale in Ka and time in milliseconds. All faults below the green line of this magnitude and this duration, there was only superficial smoke damage. All faults that occurred between the green line and the red line had minor damage, and all faults above the red line were severe faults and burned through the insulation. So you can see you get as little as 8.5 Ka for 300 milliseconds or 3,000 amps for 600 milliseconds. So it doesn't take a lot of arcing damage to cause severe damage to your electrical equipment. So when you're at 40,000 amps, it takes 83 milliseconds to clear the fault, open the breaker, but you have to detect the fault. If it goes undetected, you're going to have a lot of damage at the point of fault. So to minimize the damage to equipment, and more importantly, to minimize the incident energy that your personnel is exposed to, we have arc flash relays. Arc flash relays don't rely on standard overcurrent devices to operate your breakers. They're fast detecting, light sensing equipment to detect the presence of a arcing fault and to clear the system of that fault right away. So again, for the solidly grounded system with an arc flash detection relay, we've lowered the arc flash magnitude from 6 to 1. So we've gone from 26 to 21 because of the presence of the arc flash relay. So we've put in equipment that will save personnel. So we're going to discuss high resistance grounding now. High resistance grounding involves replacing that. Typically, when you have a solidly grounded system, all you do is take that neutral point, connect it directly to ground, and you can distribute the neutral. With the high resistance grounded system, you place a resistor. On a 480 volt system, you can put a 27 ohm resistor or a 55 ohm resistor, and you limit the fault current to 10 amps on a 27 ohm resistor or 5 amps on a 55 ohm resistor. Remember, we said earlier that all faults have to return back to their source. And if there's an impedance in the source, we limit the fault current. So that same fault we had at 40,000 amps is reduced to 5 amps simply by putting a 55 ohm resistor in here. The one thing you do sacrifice is that you do not have a distributed neutral. The best part of a high resistance grounded system is the ability to locate where the fault is. So imagine if you have this, one second. You have this system, you have a resistor connecting the neutral to ground. You get a ground fault on a phase downstream. You turn on the pulsing. Pulsing is basically changing the value of the resistor. Let's say you have a 55 ohm resistor, you change the value of the resistance to 27 ohms. So now what happens is the value of the resistor changes cyclically depending on the state of this contactor from 55 ohms to 27 ohms, producing a signature that you can actually use to help locate where the fault is. So when you turn the pulsing on, only the faulted path will indicate this cyclical pulsing signature. So you can find exactly where the path of the fault is and exactly where the point of the fault is. As soon as you pass that point of the fault right there, no, you can't see it there. As soon as you pass the point of the fault right there, you're back to normal system currents. So you can find where the fault is in any size facility in less than an hour. And more importantly, you don't even have to open up any doors to do this because you can actually detect this signature around conduit. So this is the particular relay that we have. We turn on the pulsing. It's hard to tell, but if you look at that bar graph over there, you can see it changing, high, low, high, low. We're looking at the path of the fault. And I've got this around the conduit, the elbow, it's grounded. Now you've heard the expression that current takes the path of least resistance. Not true. Current takes every single path that's available to it. So you can find where the fault is without opening up any doors and exposing yourself to a greater hazard. So Junkie Jacob wrote this book, Industrial Power System Grounding Handbook. And he stated that most faults begin as single phase to ground faults, and 95% of all faults begin as single phase to ground faults and then propagate to a three-phase fault. So by converting to a high resistance grounded system, you've created a safer system and minimized the damage to your equipment. High resistance grounding helps ensure ground faults of a known magnitude. So you don't have between 20 and 50,000 amps of ground fault current. You know when there's a ground fault, you're going to have 5 or 10 amps of ground fault current. High resistance ground provides the same advantage as ungrounded system, but limits the fault current to a low value, 5 amp, providing you a means of locating where the fault is and clearing the fault in a timely manner. So that same facility that we saw in Michigan, where we experienced 485 peak events over 700 volts, after converting to a resistance grounded system, had 0 peak events over 700 volts. So if we look at our electrical standards for safety, high resistance ground, a great majority of electrical faults, this is what I said earlier, high resistance grounding is an arc flash mitigation technique. Now, this is where we have to have some differentiation. It does not lower incident energy. All it does is reduce the likelihood of exposure by limiting the fault current to a low value, whereby the ground fault will not propagate to a face-to-face fault and create a three-phase fault. This is on systems up to 5,000 volts, 5 kV. If you limit the fault current to 10 amps or less, you have an arc flash mitigation technique. So a standard HRG system, the minimum requirements are resistor to limit the fault, ammeter to detect the current, voltmeter to measure the voltage, pulsing contactor. So for a data center using a standard HRG system, typically you're going to have a transformer, a generator, you're going to have a high resistance grounding system on each, because most people who supply high resistance grounded systems are going to have a high resistance grounded system for each resistor. You're going to have one on the transformer and one on the generator, because believe me, no one can withstand a ground fault more than a data center. And we use them for hospitals in Canada. So with a standard HRG system, your unscheduled process interruption is 1, their ability to locate the ground fault is 1, loss of critical process due to a second fault is high because you can't detect that second fault. Capital equipment damage is medium, frequency is low, arc flash hazard when a second ground fault occurs is medium. So you're at 16. The smart HRG system, now the minimum requirements is a resistor to limit the fault current, a pulsing contactor, option for resistor monitoring, because one thing we have in Canada is you have to monitor the integrity of the resistor ground path. If that resistor fails short-circuited, or if the path from the neutral point to ground has a ground fault in it, you're going to have a solidly grounded system. If it fails open, you have an ungrounded system. Easier fault location. Now we have the ability to put in SIFT, selective instantaneous feeder trip. So we can monitor every single feeder to detect the presence of the fault and isolate the feeder that the second fault is on in a timely manner, and an arc flash monitor. We have one thing we've done is we've listened to our audience and said, it's great that I have a high resistance grounded system and I decrease the probability of having an arc flash event, but I want to reduce the severity of having an arc flash as well. Why am I spending the money on a resistance grounded system if I don't get both benefits out of it? So we've created a arc flash monitor to clear the fault in a timely manner and have the benefits of decreasing the probability of having a fault as well as the severity of having a fault. When you do that, everything goes to 1 and your risk assessment meter is at 6. So this is the way it looks in the same data center. Now we have 2 resistors and 1 high resistance grounded system on the actual distribution system. So we have a 0 sequence CT on each one of the breakers, and we can monitor which feeder has the fault. If you saw my example previously, we saw that the fault was on A phase on feeder number 3. So this would have feeder number 3. We start looking downstream from this point to find where the fault is. If a second fault occurs on a different phase or on a different feeder, these 2 feeder modules will communicate with each other, and the one that you program to be of a lower priority will trip first. The reason why I have only 2 resistors here is because the ground fault current is going to return back to the source. When you're here, it doesn't matter if the source is a transformer or if the source is the generator, the ground fault current will go back to the source. So we only have to have 2 resistors and 1 HRG system to protect your entire system. So reduce the likelihood of exposure, high resistance grounding, add an arc flash monitor relay, reduce the severity of exposure. These are some of our additional products that we have. So we cover for ungrounded system, resistance grounded systems, and we have relays for solidly grounded systems. So why partner with I-Gard? Because we're the best in the market. Again, if we compare ungrounded, solidly grounded systems, high resistance grounded systems, smart HRG and smart HRG with the ADM module, you get the complete line of protection. Any questions? You guys can hear me.
Thank
right?
you, Sergio. That was really good to go through all that. And as a arc flash instructor, this is something we discuss all the time, because as you said, that one slide there where you showed the rise in damage for arc flash in timelines. I mean, at a 1 cycle, arc flash event, you'll have a little bit of a smoke coming out and perhaps a little bit of spark. But something you have to remember is that during an arc flash event, you have 10,000 degrees Fahrenheit of burn at the actual initiation point. And so you're going to start melting copper, and as the copper melts, it vaporizes. That's what creates your huge amount of force during the arc flash event. So as you start getting into 2 and 3 and 4 cycles, of course, there's more burn time, more force and explosive power coming out of that arc flash event. And by the time you get to about 6 to 10 calorie or 6 to 10 cycles, you're into a major fault where you're looking at basically total destruction of all your switch gear. So with something like the I-Gard system that can trip this at, I think the term was about one cycle to 2 cycles, Sergio? It was very quick noise in milliseconds.
With the arc flash monitor, we can trip in less than 100 milliseconds. One millisecond to detect the presence of a fault, and then 5 cycles for the breaker to open, right?
So it's a massive a drop in your explosive power and damage to your equipment. We've got here from MS or Mike Shelley. Will your equipment work on a DC system?
We do have DC high resistance grounded systems. It's a little bit harder. Well, first of all, if your DC system is a floating DC system, we can do it very easily. If, for example, the negative rail on your DC system is grounded, it becomes a little more difficult. So it depends on your DC system, the grounding of your DC system to begin with. But we do have In fact, we have a manual, we have a DC sleuth that we've put in for some apparatus. We have actually put in some places in, I forget the name of it, but it was an electrolysis place. So where they use a lot of electrolytes. So we can find with the DC system, in that type of system, you can tell exactly where the location of the fault is. Because if you have a plus or minus 125 volts, a 250 volt system, when you get a ground fault, if it's a floating system, you shift the voltage with respect to ground, much like you do with an AC system. But yes, we do have those systems.
So Sergio, a lot of your talk there is about different grounding, grounded systems, etc. And one thing I've had in my career is grounds, the actual resistors faulting. And if we had something like your I-Gard system, would that detect the fault a lot quicker and maybe put a lot less stress on our resistors at fault? Because I know that it causes catastrophic damage when you have one of your grounding resistors blow up.
Well, with our system, we can actually monitor the integrity of the resistor, and you get an alarm before you have a fault. One thing we have to do is monitor in Canada. One of the rules is to monitor the condition of the path from the neutral bushing of your power source to ground if it becomes open or short circuited before you have a ground fault. So even before you energize the power, you know if there's a fault in the system.
Great, because that's when you have something like that, you're down usually for anywhere up to a half a day by the time you source a new resistor and get everything isolated and grounded and put your system on track. So we've got another so Mike Shelley says thank you. Are a lot of DC in the solar fields, and it's a big deal for us. I'll visit your website. So sort of answered that question there. So does anybody else have any other questions? I just for those that joined late, I put the PDF in there. Sometimes you might have a problem downloading that. If you do, please visit us Electricity Forum and just write an email to Louisa, and she will email the PDF to you. Because sometimes your corporate computers will have some problems opening up this because of cybersecurity, etc. So no more questions?
All right, thank you, everybody. It's been
Okay.
great, but time for someone else to take over.
Okay, thank you so much, Sergio, and have yourself a great day.
Thank you.